It's good to see y'all in Finland. And the talk that I'm giving is going to be a continuation on some of the ideas that Jari was already talking about in green computing, talking hurricanes, hammers, and HTML, or in practical terms, actually measuring the carbon emissions of the websites that we build. Now, to introduce myself a little bit, I'm Ben. That's my face, but bigger. And I'm a senior developer over at Astro, which is a web framework for building content-driven websites. So if you build homepages, blogs, docs, that's the kind of thing we specialize in. So it's definitely something I'd recommend. I'm also a content creator, which he was mentioning, president of Whiteboards, because I do a lot of whiteboard explainers over on YouTube and Twitter and other places. And that is my handle if anyone wants to follow me after the talk. And crucially, I'm an American. I was told coming over here that y'all are very rambunctious and try to crowd the stage with questions. So I ask that you calm down, save the questions till the end, and then we'll get to them. OK, it looks like we're good. All right. So the key takeaways that I want y'all to walk away with. First off, we're going to talk about the 3 main energy consumers if you break down usage of a website. And we'll talk about the standard page weight model that gets represented a lot when you use carbon emission tools. Also, like bytes transferred, data transferred. You may have heard that term before. And we'll actually talk about the flaws in this model, since it's a very early area of research, and there's a lot of gaps and assumptions that go into actually figuring out energy usage. And we'll try to improve on this by modeling out energy usage across data centers and user devices a little bit more effectively with the code that we write. And all of this is an invitation for y'all to explore this area of research. If you see holes to poke in any of our presentations, that's probably expected, because it's a very young area of research. It's called future front-end for a reason. This is very forward-looking. So we'll leave y'all with resources and hope that you expand on those with the things that you build. So the motivation for me in doing this talk, since I am no climate expert, at least starting this talk, was this website that's made the rounds called the website Carbon Calculator. You may have seen this before, but I can show you right here. This is, oh, shoot. Let me join this network right here and see if we can get that pulled up. 1 second. All right. There we are. The, oh, is that not going to show my display? Interesting. All right. That might be an issue. I thought it was going to share everything. Which desktop is that showing? Sorry about this, y'all. We only tested the PowerPoint, and we didn't actually look at the code demo. Always unit test everything. All right. Let's look at displays. And we'll see right here we have a built-in display. And, oh, interesting. OK. So we have VP. And we have that. Can I change the main display? I cannot do that. All right. If we change this over here. Sorry about this. Does anyone have a good joke? Are any Finnish people good at jokes? Any hands raised? OK, not yet. I'll keep going then. Preset. I'll choose Apple Display. That
I can tell a joke if you want me to kill time.
All right, go for it.
So this is an old joke from Soviet Russia. A man goes to buy a Lada. It's the Russian car they used to make. It's about year 1985. So he goes to the Lada dealership and goes, "I would like to buy a Lada. I've been saving this for a long time." And they go, "Yes. Let's see. We can deliver this on Wednesday, 2nd of February in 1995." And that goes, 10 years? It takes me 10 years to get a Lada? Goes, yeah, that's the way it is in Soviet Russia. And guy goes, "OK, but is it going to be the morning or the afternoon?" And the dealer goes, "What does it matter?" "Well, I have the washing machine repairman coming in the afternoon, so I'll be busy that day."
Nice. Nice. That is probably going to be the highlight of my talk, actually. That's the best joke you're going to hear all night. And we got it working. There we go. OK, so this is what I was trying to show you all a little bit earlier. This is the Web Carbon Calculator. And it's a very simple tool. It just takes in whatever page URL you might want to visit. And if you hit calculate, it just goes off. It tells you a fun fact. And then eventually, it just kind of loads results based on the website that you're visiting. Looks like it disconnected me from Wi-Fi while we were doing that. Cool. One moment. Let's see if we can get that again. Refresh. And if we calculate, that should go off to the cloud, compute a little bit of information, and then as soon as that comes through, it gives you a rating based on whatever website you pop in. And apparently, my personal site gets a rating of B. I guess that's B for Ben, which is the best score that you can get. And you see it's 73% of all web pages globally, cleaner than those. This is an approximate usage of CO2 to display that web page once in someone's browser. And it appears to be running on sustainable energy because it detected what host that I was using. And it gives you all sorts of fun facts to put this into concrete terms, like saying it's equivalent to 4,000 cups of tea, all sorts of fun facts that you can bring to product managers to improve the performance of a website. It's meant to spark a conversation. But if you're like me, you might be a little bit skeptical reading this. Like, I just put in a URL, you know nothing about my infrastructure or my servers, and you gave me the exact energy usage. That seems like there's a lot of approximations or other things. I'm curious how that works. It's also something that we use at Astro ourselves. This is our Starlight documentation site, which is a tool for building documentation. And one thing that we tout on our landing page is actually the green usage. We say they are eco-friendly docs, because when you compare energy usage using that tool I displayed and compare it against other popular code-based, markdown-based frameworks, it seems like we're at the top, because we just ship plain HTML. We don't ship any scripting or other resources unless you opt into those. So if you just use the base case, type in your information, then you'll notice a very low energy usage. And, you know, on paper, that sounds great. Less compute means less energy. But what goes into actually getting those numbers? And how accurate are those numbers really? Well, let's dig into that a little bit. Tracing down what the carbon calculator is, it's created from the Sustainable Web Design model. And this is created by the Green Web Foundation, which is a nonprofit that builds open source tooling and research and blog posts, all sorts of things detailing the space of green computing. And they break down energy usage into three main metrics. These are the three that I alluded to. User devices, which accounts for about 54% of energy usage globally. Pretty significant figure since there are just so many devices in the world. And the rest is accounted for by the infrastructure. The networks that are shipping your code around the internet, and the data centers that are running your compute and managing your databases. And if we split these apart, we can actually break down the energy usage of each of those. And before that, I should at least do some ground setting. Of course, data centers, that's where your app's going to live. We're talking about cloud services whenever we say that, AWS, Google Cloud Platform. Or if you're hosting on a CDN, you might also consider the usage of Cloudflare and other proxies that you have set up. Depending on your infra, that can be a very complicated piece of the pie. Or if you're just deploying to AWS US East, it's a very simple one to calculate. And then network, as you know, this is going to be your Viasat, your HughesNet. I had to Google what Finnish network providers were. I hope that's right. AT&T, you know these. This is actually transferring things from point A to point B. And user devices are going to be, you know, a wide range of devices from the most power-hungry desktops to the smallest mobile devices. And all of those have very different energy profiles that you might want to consider. Like if you get a lot of mobile traffic, some things matter more than others. If you get a lot of desktop traffic, you have a different set of concerns. So there's all sorts of weights to consider. And when you actually want to measure energy usage, you're going to consider bytes transferred, otherwise known as page weight. This is what the Sustainable Web Design model might nudge you to do. And it's pretty simple on the face of it. You might take all of the bytes that you're transferring over the wire. In this case, maybe we have 2 gigabytes of assets sent in a given day, or all at once if you have a really huge 3JS application across all of your assets. And then you multiply that by the cost per byte, and that's something we're going to break down. And those are going to be the cost factors in energy usage across each of those 3 metrics: data centers, networks, user devices. And if we wanted to calculate that cost, we could take each of our components and calculate 2 big metrics. The first one is operational cost. Operation is literally operating expense in business. It's what it costs to keep the lights on. So all the compute running on AWS in an EC2 instance that you spun up, that's going to be the operational cost. Also a SQL server or other components. And then embodied is going to be the manufacturing expense. This is what it costs to actually build the server rack that AWS is using. It's not a cost that you incur, but as CPU needs increase, of course, they have to make more servers. So you probably want to factor that in at a macro scale to say, if we increase the CPU usage of every website tomorrow, embodied costs are going to go up as well, because we got to go make more servers. And this gives you a nice total for that component, and you can divide all of that by all the bytes that have ever been transferred on the internet in the past year. It's crazy that this number exists. I don't know how you compute that, but Sustainable Web Design seems to think you can. So in their metrics, they take all the bytes transferred ever and divide that against the kilowatt hours being consumed, and that gives you a factor that you can use against all your bytes transferred. This is going to be kilowatt hours per gigabyte for that component. And then you can compute that for each of the 3 other components to plug into a model. And I've shown some color-coded averages to show the scale of these. Of course, mobile is going to be a lot higher because the embodied expense is a lot bigger. There's a lot more turnover in all of the iPhones that we're using year over year. Amazon is going to stretch a server rack to its absolute limit and maximize its usage. But someone who owns an iPhone 12 Pro, they're probably not doing very pro things. They're just buying a nice camera and then maybe switching it 2 years later. So the embodied expense is going to be a lot higher for those people, embodied being manufacturing. And each of these factors can scale up and down depending on what resources you have. If you, for instance, use a green host instead of a standard host, then your data center cost might be lower. If you don't know what a green host is, it's not a concrete term, but it often means carbon neutral if you're working with Google Cloud Platform or Cloudflare. Each of those actually have options in their dashboard to say, I want to run this job on a clean host instead. So if you have cron jobs and you don't care about where they run, you don't care about network latency, you just want them to be efficient when they run once per day, you can ship those to a green host, and you can reduce your emissions a little bit. And you also might have a little variation in the network, depending on the location that you're serving. For example, if you're serving traffic in India, that's going to use maybe 3 times as much energy as serving that same traffic to Europe or to the United States, because the infrastructure in that country is running on much less sustainable energy compared to Europe or other places. And the last one, user devices. These are going to vary based on mobile versus desktop, as you might expect. Mobile devices are more solid state and efficient, so depending on your users, that can scale as well. So let's make it a little bit more practical. We'll take those 2 gigabytes that we were sending over to Wire earlier, and we'll push those through all of the metrics that we have. So it's a simple multiplication when you're using their model, where you take the 2 gigabytes, you multiply against this factor, which is kilowatts per gigabyte, and then you get an approximate amount of watts that are being kicked out every time the data center processes those. Same goes for the network, same goes for user devices. You can take all of those values that you computed, add them together, and you get a rough estimate of how many kilowatt hours are being consumed end to end when we're shipping all those assets every day. Now, I'm going to stop and ask a question. Who flew to get to this conference? Who flew? Oh, a lot of people. OK, you over there. Oh, sorry, keep your hands raised. I was actually going to call on people. Yes, yes. How long did it take you to fly here? Like how many hours, roughly, travel time? 8 hours? OK. Someone else. Yes, in the front. 3 hours? All right. 2? OK, so we have 8, we have 2, we have 3. You can put your hands down, sorry. That's a pretty wide range of different flight times. But that doesn't make sense to me, because I ran the numbers, and I thought everyone took 12 hours to fly here. Because I used the page weight model to compute this, and I thought, OK, how many bytes do we have? Well, we had about 300 attendees, so that's 0.3 kilohumans, maybe. And then we took how many hours the conference is. We have workshops and other pieces. That's about 40 hours per kilohuman. And then I multiplied those together, and I got 12 hours. You telling me this isn't right? Tell me there's something wrong with this model? Well, I'll admit, when I actually ran that, it felt the same way the Finnish language did to me for the first time. It seemed like gibberish. I don't understand what this is. I don't know where this is coming from. And that's because, to sum it up very concretely, destination is not the same as journey. We were all going to the same destination, Helsinki, and we all are transferring the same bytes ourselves, but the journey to get there is going to vary a lot between all the transfers that we take, the origin that we're flying from, the flights that we're going on. All of that can dramatically change the amount of energy usage we use. You know, Jari was talking earlier about how aviation is a major factor as it is for IT. So we know that there's something amiss here. Bytes transfer may not be the best scaling factor. And the experts kind of know this. Debugbear is a web monitoring service that offers a whole lot of calculations, including core web vitals, lighthouse scores, which you might have worked with. But they don't include the CO2 calculations. And they wrote a very extensive post on why that I recommend you read. But a big takeaway, none of these metrics and their findings are meaningfully correlated with page weight, which is a very dramatic stance that actually does have some weight to it, some page weight maybe. And, you know, we'll break that down by each component. Data centers, for example. This is a playlist that I was listening to while preparing the talk. It's a great house playlist if you're a programmer. But you can look here, you know, if I'm keeping it really simple, and I say, to display all this playlist on the page, I might do a simple SQL query that gets everything in the playlist where the name is that. But what if there's other factors? Like, what if we forgot to index the name field? Well, we transferred the same amount of bytes, but now the kilowatt hours are probably going up because that SQL server is operating for a bit longer. And then what if we're joining with other tables? Now it's getting even longer. And what if we're filtering by US-only tracks? The kilobytes actually went down because we have fewer tracks that are being rendered in my browser. But the compute definitely increased further still. It doesn't capture the work on the server to look at the output. And there are actually different reasons this doesn't scale super well for network activity. There is some nuance here, but from a researcher at Zurich, there was this notable study on typical network devices. Looking at those in isolation, you find that the actual amount of traffic on the network is almost independent of the traffic load, which means if you're looking at this power graph here, looking at no utilization of the network to maximum traffic on the network, and then looking at the power draw on the other axis, you see that it's a pretty shallow slope. From 0 to 1, there's a pretty constant rate of activity. That's because it's consuming about the same amount of energy to just keep the network running, but as you increase the load on it, it's not really going to scale up. So it's a bit dishonest to say there's this one-to-one relationship between the bytes that you're sending across the network and the energy that you're consuming. So it might be overrepresented in our model. And as for user devices, bytes transferred is somewhat of a proxy of how much compute the user's device is going to do, but not all bytes are created equal. You probably know that a really inefficient JavaScript program that says while true is going to consume way more energy than a 100 kilobyte JPEG that you're just rendering in the browser, or 100 kilobytes of HTML. So the bytes matter, but the weights of each one should probably be considered as well. And devices aren't created equal. We already discussed mobile devices are a bit more efficient, so treating all traffic as the same can be a bit dishonest. And there's different factors on these devices as well, because mobile devices are really smart about CPU usage. They don't use a lot of CPU by comparison. But funny enough, the most important factor on mobile, because CPU is really efficient, is the display brightness. If you crank the display brightness on a phone, you might have noticed that it dies quicker. And that also translates to energy usage. You're going to be ripping through the battery faster if you crank up the brightness. So in a funny way, this might be a reason to add dark mode to your website if you needed a reason other than accessibility. At least for OLED panels, it does reduce energy usage pretty dramatically. But for other aspects of your website, CPU might not be the thing that you're tracking. So there's definitely some nuance that we want to think about. Now, one credit that I will give to bytes transferred and embodied is the actual usage on a phone. If you look in the last 10 years throughout the mobile computing revolution and kind of the JavaScript revolution as well, the weight of a mobile page has gone up almost sixfold. And there's a correlation between that and maybe the turnover of the devices that we have. And a practical example if you ship a massive 3JS demo, you might pull it up on your grandma's Amazon Kindle and notice that it's really chugging and failing to render. Or if you pull it up on a feature phone or an older Android device, that's not going to render well either. And there's this kind of cat and mouse situation where people are building more and more intensive software, which is requiring people to constantly replace their devices. Sometimes to just get the newest features on the latest iPhone, but also to just make sure things in the browser stop locking up on them, or other excuses that I've heard family members make. I've got to buy a new phone because it's locking up, and I can fix it. No, I'm going to go buy a new phone. That's not really a great problem to have, and it's something that we as web developers can at least try to solve on a macro scale. So, with all of that in mind, looking at data centers, looking at network, user devices, how can we measure? Ask the same question again. Well, we probably want to use the best metric for each step, best scaling factor that we can think of. If we look at our approximations, maybe we add some new weights to each of these. First off, for data centers, you might want to consider CPU time instead. Not the perfect proxy, nothing is, but if we wanted something that scales, close-ish to 1-to-1, we might measure the amount of milliseconds that are running in middleware for each of our server operations. And there's been some meaningful research on that. Yari was mentioning earlier about a study on code smells, and if you resolve code smells, there's a meaningful correlation to energy usage. That's kind of true across the board. If you think about it, if you make your backend faster, more efficient, it's probably going to consume less energy. So let's try to use CPU time to figure out that weight a little bit better. It measures performance, user experience, and climate in a decently accurate way. As for network, you might want to treat that as constant when you're designing your app for the first time. Since it is fairly constant usage with today's data center racks or network racks, it's probably best to just kind of exclude it from your model, not worry too much about how you are affecting it. But it is still a factor you might want to consider on the macro scale. And for user devices, you may still care about bytes transferred, what we talked about earlier. But try to weight it based on the type you're sending out. If you have a JavaScript file that's very intensive, you might weight that higher in your calculations compared to a JPEG, compared to an MP3 file. And sending it across the wire, you might hit very different measurements. Like that is 3 times the metric that we had earlier for data center usage because we were looking at CPU time. And that difference might be enough for you to look through your calculations and decide, oh, it looks like data centers are accounting for over 50% of my usage. Maybe that's somewhere I want to start. Make my backend faster, and then I'll worry about the bytes that I'm transferring afterwards. It helps you focus your efforts after you're in the door. And again, that could give you a different value so that you know where you got to focus your debugging efforts. All right, let's try to do a little code demo. You can see right there, there's a link, wtw.dev/climate. If you want to see the source code in its completion, this is a link to a little GitHub repository. So if you want to look at the middleware, all the code comments, I'm also linking some resources in there. You can definitely head over. I'll highlight that link again at the end, and we'll try to code it live so that we can also see how this experience works. I'll open up my editor right here. And this truly on-brand is an Astro website. We're going to be checking this out over here. This is a very simple website that's just meant to be a soundboard generator. So, in the middle of a Zoom call, someone's falling asleep and you want to hit an air horn button. That's this purpose. You can upload an MP3 and hit play. And building this, I wasn't really thinking about energy usage. I was just thinking about, let's just go build something cool. And I tried to plug some of these ideas into this app to see what we can get with CO2. And I have a metric up top for CO2 usage, which is going to be a rough estimate. I'll walk through all the constants that we're using and anything that is, something I'm more or less confident in. Heading over to our middleware function, this is where we're going to measure all the usage for our app. So you can see right here we have a lot of constants. We'll explain those, don't worry. But this is where we're defining the middleware, and this is going to wrap around all the requests that go out from this server. So we'll start by clocking the start time, say this is the millisecond timestamp when we started calculating things. Then we're going to run our server logic, and then we're going to roughly compute how much CO2 went out trying to run that job. And we have a little bit of database writing so we can persist these metrics, show them visually. But these are the 2 functions right here. Get the server CO2 and the client CO2. So to implement this, we can first start by getting the amount of time that has elapsed. So if I wanted to get performance.now, for example, we can subtract from the start time, and that'll give us how many milliseconds went by while we were running on the server. Then the number of hours would be, a little bit of division to get there. And then for the actual usage, we can compute the kilowatt hours. This is where things get a little bit interesting, because how do you figure out the amount of kilowatts that a CPU used? Well, you got to know the hardware that you're on, first off. We're assuming that we're on AWS, we're on US East, and to get the kilowatts, we're going to take this metric right here from a pretty intensive reverse engineering study. This is linked in the source code if you want to check it out. But this went through an EC2 instance and really drilled deep on how much a CPU is going to use. I just took the number for the memory-intensive task, since JavaScript is a more memory-intensive language, and I put in a fudge factor of about how much of that CPU our job is going to run. Since we're on serverless, it's very hard to predict how much a serverless job is going to take from its host machine. I know Yari does not approve of a fudge factor number, but this is my demo, okay? Trust me. You can probably improve this if you actually know your serverless bill, though. That will tell you your CPU usage. Plug that in here if you're able to. And we can take that kilowatt hour right there and return it based on the actual amount of CO2 that we are using. And this is going to be multiplied by the amount of grams of CO2 AWS pumps out. Believe it or not, there is a spreadsheet that has been provided in this open source community over here. Google Cloud Platform provides this from the platform. AWS, we had to reverse engineer it. But I say we. These talented developers were able to do so. And it gives you a rough conversion from kilowatt hours to the CO2 that data center would pump out. Since we know where we're hosting, we can do that. If you don't know the region that you're hosting in, you might want to ignore CO2 and just keep things in terms of kilowatt hours. They'll give you the exact same amount of information. We're just doing this because, well, CO2 is the direct measurement that we're trying to go after. So we can be accurate, let's be accurate. All right, and now we get a little graph in our UI that's showing us server usage. It's not scaled, so let's look at our client usage to make sure we also have that metric. I'm going to take the amount of bytes that we're sending over to Wire and multiply it by the amount of kilowatts a gigabyte might consume. This is coming from Sustainable Web Design, and they're just giving a global average of how much CPU a user's device roughly uses. Super rough. If you have analytics, you can definitely improve that number, but a global average is a good starting point. And then we can take that and multiply by another factor from Sustainable Web Design to get that CO2 number. So if we plop that in here, now we get a rough average of, OK, this is how many bytes were transferred, this is the server usage, and we can see a ratio to compare everything that we're working with. Now, let me try uploading a few sounds here. If I, upload, that sound effect, that one, these will go up to our server, and you get some CPU usage trying to upload those. And something you'll notice when you hit play on each of these is you'll see a little spike in activity as we're downloading the bytes and playing the audio for the first time. It makes sense, but I wouldn't expect to get that cost every time I visit. You'll notice that we are getting a spike on every visit, but these are static files. Why are we getting a spike on every file? Interesting. Well, I did forget what a cache header is, apparently, so that helps me debug that issue. If we head over to this file, this is where we're serving everything out of a bucket, all those audio files, and looking at that energy usage, I was able to debug, maybe I should put a little cache header in here so that I'm not wasting valuable resources for repeat visitors. This is saying just cache it forever because this audio file isn't going to change over time. It can only be created or removed. So that's a pretty safe cache to add for our purposes. You'll still get a spike for the initial visit, but once the cache is registered in your browser, you should now see that there is no spike. So there you go. Nice way to use a debugging tool and figure out where your energy usage is coming from. There is one other demo I can give. I know we're running a little bit long, but what's that? We're good on time? Sweet. All right, well, I will go normal pace. So the second thing that I wanted to talk about is, well, yes, we are able to cache things effectively, but what if you upload something really, really big? Or honestly, something moderate. Here I have a 15 megabyte file that's about 4 minutes long. It's an opening track. And it looks like this website just lets me upload 4 minutes, and it's totally fine. Well, let me go ahead and hit play on that. And oh my God, that's a lot of bytes. And you'll notice as things are playing back in my browser, it is still an ongoing stream of audio. And that doesn't play well with cache headers, I've learned. So if I refresh this and hit this, even though it's cached, it's not able to cache the resource until the whole audio file has streamed through. So not only are we allowing a lot of bytes to go back and forth over the network, we're also letting you kind of bust caches by having long files you probably aren't going to play to completion. Luckily, we have a very defined scope for our app. We know that this is a soundboard builder to play air horns and 5-second snippets. So we probably shouldn't allow really large audio files. If we head back over here, we can update our backend to maybe impose a byte limit of some kind. I have a very strict limit that I put on here, 500 kilobytes. So if any user tries to upload a really big file, we probably want to bounce it back to them and say, send something smaller, compress it as an MP3, do something, because we probably don't want to serve this. So if we say, if the byte length, which is something that you can get on a file upload, get the byte length, if that's greater than 500 kilobytes, then probably just return some sort of response. In Astro, you can update the status code while you're rendering something, which is kind of cool. If you wanted to show like an error message, we can set the status and then react to that status inside of our page. And I'll put everything else inside of an else block, because we don't want to persist in the database if something is too large. And you can see down here, I have a little banner that's going to pop up whenever that status is 413, which is a status code for invalid resource. If I refresh this again, and I try to upload that same file from earlier, you can see now, file too large. There we go. So now we're blocking bad bytes being sent over the wire. Another case for looking at the bytes you're transferring so you can actually figure out how to make your website more efficient. OK. That is the end of my practical demo. I'll try to leave y'all with a couple resources. Again, if you want to see this code and you want to copy it into your own Node.js backends, this is a pretty generic JavaScript tool. You can go to wtw.dev/climate. If you head over there, this will redirect you to the actual source code for what we just built. You can walk through the entire repository and try it locally if you want. No API keys necessary. And you'll see all sorts of embedded links for sustainable web design, which is the model we've been alluding to. Shout out to Sustainable Web Design for having a very clear breakdown of how their algorithm works. All those calculations I ran are this math table. They tell you absolutely everything about each component, where the numbers came from, how to multiply it yourself. So if you want to go back to algebra class and practice things, there you go. And we also have a couple other links in here. The Medium article for reverse engineering AWS, pretty useful. And the cloud footprint, which is our timetable for all energy usage across cloud providers. It's something you can plug into your own setup if you know the hardware that you are using. OK, I think that's everything I wanted to get through. I will leave the floor for Q&A. Thank you so much. Appreciate it.